In a previous video, I looked at how to prove Pythagoras' theorem and showed that for any right-angled triangle, the square of the length of the hypotenuse is equal to the square of the lengths of the other two sides. So for this triangle, a squared plus b squared is equal to c squared, where c is the hypotenuse. I'm going to look at some questions involving Pythagoras. But before I do, I want to think about the use of letters and notation more generally in such questions. I'll show you what I mean. Here are three triangles, and I'm going to write down Pythagoras' theorem in the context of each triangle. The objective here is to get you thinking about the formula a squared add b squared is equal to c squared, what it means, and how it might present itself in a question. You need to be comfortable with the theorem and understand that the square of the length of the hypotenuse, the longest side, is equal to the square of the lengths of the other two sides. So for the first triangle, we have the sides x, y and z. Z is the hypotenuse. It's the longest side. So x squared plus y squared is equal to z squared using the formula. You could, of course, write this as z squared is equal to x squared plus y squared. In the next triangle, we have the vertices labelled. The longest side is the side RQ. So RQ is the hypotenuse. Therefore, RQ squared is equal to the square of the length of the other two shorter sides, which is PQ squared add PR squared. And finally, we have this triangle. Notice that the length of the two shortest sides are given, and that's it. Well, what we can do here is allocate a letter to the side that we are trying to find, which in this case is the hypotenuse. Well, let's label this side C, since the formula is a squared add b squared is equal to c squared. But you could use the letter H, for example, H for hypotenuse, or say the letter X. As long as you understand what length you are trying to find and how it relates to the formula, that's the important thing. So if you did use the letter H, then we would have 5 squared plus 12 squared is equal to h squared. But we are using the letter C, so we have 5 squared add 12 squared is equal to c squared. Or I could write this as c squared is equal to 5 squared add 12 squared. Again, and I alluded to this in the previous video, that when labelling the sides of the triangle, we use the lowercase letters, and we use capital letters for the vertices. C squared is equal to, well, 5 squared is equal to 25, and 12 squared is equal to 144. 25 add 144 is equal to 169. C, therefore, must be the square root of 169, which is equal to 13. And that's the answer. So notice that we have a right-angled triangle with the sides 5, 12 and 13. This is what we refer to as a Pythagorean triple. The 3, 4, 5 triangle that we looked at in the previous video is also a Pythagorean triple. This is a set of three integers that satisfy the equation a squared plus b squared is equal to c squared. We'll come back to this later. Let's have a go at another question. If you wish, feel free to pause the video and have a go at the question yourself before I go through the answer. And press play when you are ready. So, one of the shorter sides is 9 units long, and the hypotenuse is 15 units long. Let's allocate a letter to the side we are trying to find. I'm going to use the letter A, but you could use any letter. Now it's useful to start with the formula. So let's write down a squared add b squared is equal to c squared. So we have a squared add 9 squared is equal to 15 squared. So that's a squared add 81 is equal to 225. We need to find a squared. What, when added to 81, is equal to 225? Well, that something must equal 225 subtract 81. So a squared must equal 225 subtract 81, which is equal to 144. And we know that this is correct because 144 add 81 is equal to 225. So what number, when squared, is equal to 144? And of course, if you know your multiplication tables, the answer is 12. 12 squared is equal to 144, so the missing length is 12 units. And we have another Pythagorean triple, 9, 12, 15. Do you spot a relationship between the sides of this triangle and the 3, 4, 5 triangle? Well, 9, 12 and 15 are multiples of 3, 4 and 5 respectively. If you multiply each of the numbers 3, 4 and 5 by 3, you get 9, 12 and 15. And this is one way of generating Pythagorean triples, by multiplying the sides of the 3, 4, 5 triangle with the same number. So if I multiply 3, 4 and 5 by 2, I get 6, 8 and 10. And if we try this in our formula, 6 squared add 8 squared is equal to 36 add 64, which is equal to 100. And of course 100 is 10 squared. So 6, 8 and 10 satisfy Pythagoras' theorem. If I multiplied 3, 4 and 5 by 8, we get 24, 32 and 40. 24 squared add 32 squared is equal to 576 add 1024, and this is equal to 1600. And of course 1600 is equal to 40 squared. So 24, 32 and 40 also satisfies Pythagoras' theorem. Finally, let's look at Pythagoras in 3D. Here's a box. The width, breadth and height are 4, 5 and 3.5 units respectively. What is the length of this line? I'll begin by labelling the vertices. I'm going to start with the letter A and work my way around. I've labelled the vertices this way, but you could have labelled it differently. The key here is to assign each vertex with a different letter, and ideally there is some logic to the labelling. Try not to label randomly. If you look at how I have labelled the box, hopefully you can see the logic in my labelling. Again, notice that I'm using capital letters. Now that we have labelled the vertices, we can see that we are finding the length of the line DF. So how can we use Pythagoras? Let's add some other lines to create a right-angled triangle. We now have a right-angled triangle BDF, where DF is the length of the line we are trying to find. Using Pythagoras, DF squared is equal to BF squared add BD squared. We know that BF is 3.5 units long, so DF squared is equal to 3.5 squared add BD squared. So we need to find the length BD. But how do we do that? Well, BD is the diagonal of the base of the box, which is the rectangle ABCD. We can create another right-angled triangle, ABD. Again, using Pythagoras, BD squared is equal to AB squared add AD squared. AB is 5 units long and AD is 4 units long. And these are the two shorter sides. So here we have 5 squared add 4 squared is equal to 25 add 16, which is equal to 41. So BD squared is equal to 41. Let's leave it like that for the time being. I'm going to go back to the calculation df squared is equal to 3.5 squared at bd squared. We have just worked out bd squared, which is equal to 41. So df is equal to 3.5 squared at 41. 3.5 squared is 12.25. So we now have 12.25 at 41. And this is equal to 53.25. Therefore, df squared is equal to 53.25. And df must be equal to the square root of 53.25. And this is equal to 7.3 to 1 decimal place. We can actually create a rule for finding this length. If A is the width, and B is the length, and C is the height, and D is the length we are trying to find, then D squared is equal to A squared add B squared add C squared. Here's why. We know that to find the length D squared, it must equal C squared, which is the height, add BD squared. Now BD squared, which is the hypotenuse of the triangle ABD, must equal A squared add B squared. Substituting this into the above equation, we now have D squared is equal to C squared add A squared add B squared, which we can rearrange like so. And there we have it. D squared is equal to A squared add B squared add C squared. So if the measurements of the box were 5 centimeters, 7 centimeters, and 4 centimeters, then the length D squared would equal 5 squared add 7 squared add 4 squared, which is equal to 25 add 49 add 16, and this equals 90. So D must equal the square root of 90, which is equal to 9.49 centimeters to 2 decimal places. That's a little look into applying Pythagoras. Hope you found it helpful, and thank you for watching.